maybe face to know him because he's around here. Yeah. So Dr. Yang is right now is research assistant professor of pharmaceutical science, UNM Science Center. But at the same time, he is MRI scientist across our Brain Center. So we know him, And he got his Ph.D. in biomedical engineering in University of Illinois, Chicago. And after that, he has two postdoc fellowship experience. One is in University, Associated Northwestern University. The other is from the Henry Jackson Foundation for Advanced Military Medicine. During this experience, and he has, as far as I know, he did a lot of the animal studies MRI, and he's also kind of masters there for the animal studies. So that's why personally I'm very interested in his study. Maybe many of you is doing human studies, but animal is foundation. So likely we are very happy to have Dr. Yang to give us a talk about animal studies. Without further delay, let's continue Dr. Yang's talk.
Thank you. Thank you for having me. So, stroke is the fourth leading cause of death and the leading cause of long-term disability in the United States. Clinically, MRI, as we know, is one of the most important diagnostic tool for measurement or treatment of stroke. Besides clinical application, MRI is also used as a powerful preclinical imaging tool to evaluate potential therapeutic strategy. So, in today's talk, I'm going to present preclinical MRI in animal stroke model, particularly conducted at Brain Imaging Center. So here's the outline of this talk. First, I would like to introduce preclinical magnetic resonance imaging core as you have, which include the major instruments for animal MRI, the layout of MRI system, and the coils in the MRI system. Second, I'm going to present MRI modalities or parameters used for animal stroke models. As we know, the versatility of MRI gives us a huge advantage over other imaging tools to non-invasively measure either physiological or pathological information, which can be used to characterize the tissue status. So today I'm going to present the relaxometry imaging, diffusion imaging, perfusion imaging, and permeability imaging. Finally, I will introduce an MRI study which is used to prove the idea of attenuation of acute stroke injury in rat brain by minocycline promotes blood-brain barrier remodeling during recovery. This idea is proposed by Dr. Yirong in neurology. So here's the major instruments for animal MRI. First of all, of course, we need an MRI scanner, which provide two-dimensional or three-dimensional imaging, and spectroscopy imaging. And second, we need a small animal anesthesia delivery system, which can provide accurate gas flow to keep the animal stable during scanning. Because the instrument is at the same room as MRI scanner, so we should keep it MRI compatible. Finally, we need a small animal monitoring and gating system. Usually, this system provides physiological monitoring, including ECG, respiration, and temperature. And also, it can provide ECG or respiration gating function. We also need a heater system with temperature control to keep the animal body temperature normal. And it also has the waveform and the trend data acquisition function and the storage function. This cartoon shows the connection of all the instruments. So the animal is under anesthesia. We acquire the physiological parameters in real time, and according to the physiological parameters, we can adjust the heating system and the anesthesia system to keep the animal safe and sound. So here's the layout of MI core. Basically, we have 4 rooms. The magnet room is studied using Faraday cage technique. Most of the electronics are in the equipment room. So people sitting in the operating room can control the scanner or the electronics to set up pulse sequence and see the physiological parameters. We also have animal waiting and the recovery room for the patients. Coils in the MI system. Basically, there are 3 kinds of coils. The first is the coils to form the main field magnet. So usually when we talk about MI, we always hear, like for example, 1.5 Tesla MI, 3 Tesla MI, 4.7 Tesla MI. These field strengths actually determine the signal-to-noise ratio of the image we acquire. And there are also different bore size available on market. We have 40 centimeter bore, which is big enough to accommodate different kinds of animal. And of course, there are other kinds of smaller bore size corresponding to higher field strengths. And the coil is superconducting solenoidal design. There are bursts in liquid helium, allowing a stable, homogeneous field to be created. It is outshaded, which means we have minimal stray field, 0 helium boil off, reduced, so we have reduced the maintenance and operation cost. Second kind of coil is gradient coil. So for imaging, we need spatial information. The gradient coil usually tells us where the signal flow. In our core, we have an inner diameter 12 centimeter gradient coil and the slew rate, which means how fast to reach the maximum gradient strength. This parameter determines how fast imaging we can do. And the maximum gradient determines the best spatial resolution we can acquire for the image. Finally, RF coils. We have 2 kinds of coil. One is volume coil, which can be used a lot as a transceiver, either for brain imaging or body imaging. And we also have service coil, which is used to receive the MI signal in cross-coil operation. This kind of surface coil can significantly increase the signal-to-noise ratio. So let me move to the multiple modality MI. First, I would like to introduce the relaxometric imaging. T1 refers to the longitudinal relaxation time or spin lattice relaxation time. It deals with how efficient the protons can give off their energy to the surrounding lattice or absorb the energy from the lattice. Usually the most efficient energy transfer occurs with the natural motional frequency of the proton at the nano frequency. So here is the T1 recovery curve in the brain. Usually we have 3 kinds of tissue in the brain: white matter, gray matter, and CSF. So we can see the white matter has the fastest recovery curve, and the CSF has the slowest recovery curve, which corresponding, we can see the ventricle, which contains the CSF, has the lowest intensity. But on the contrary, the T1 value is the largest in the CSF. And the lesion caused by the stroke is fluid-like, so it has similar intensity to the CSF, either on the T1 weighted image or the T1 map, which show the absolute value of T1 value. T2 is the transverse relaxation time or spin-spin relaxation time. It reflects the defacing rates caused by spin-spin interaction. Usually higher natural motion frequency of the proton, it has the longer T2. So here is the T2 decay curve. The white matter has the fastest T2 decay, and the CSF has the slowest. Correspondingly, the T2 is larger in CSF. Proportionally, T2 values is also higher, corresponding to the higher intensity of T2 weighted image. So the major application of relaxometric imaging is to detect so-called vasogenic edema in the stroke. It usually appears 12 to 24 hours after ischemia. It happens when an increase in total tissue water content after development of irreversible tissue injury. And it has limitations because its time window is late. So it's not helpful for early confirming the diagnosis. For example, those three images are acquired within half an hour of ischemia. On the T2 weighted images, we can hardly see any signs of the lesion, but on diffusion image and perfusion image, we can see the ischemia lesion already start. Okay, let's move to diffusion image. Diffusion, also known as Brownian motion, refers to constant random microscopic molecular motion due to heat. We can simply use Einstein equation to describe this physical process. The mean squared displacement of the molecule equals to diffusion constant times the diffusion time. This cartoon illustrates the intravascular diffusion, extravascular diffusion, and exchange between intracellular and extracellular space. So one key point for diffusion imaging, I think, is the typical diffusion times used for diffusion imaging are 10 to 15 microseconds. So it corresponds to average molecular displacement on the order of 10 micron. So this microscopic spatial scale is at the same range as that of cellular dimension. So basically, there are three, we can classify diffusion into three categories. One is so-called isotropic unrestricted diffusion. The second is isotropic restricted diffusion. The third is anisotropic restricted diffusion. And no matter what kind of diffusion, we can use diffusion tensor imaging to form a tensor form, and use the eigenvalue derived from the matrix to calculate two fundamental parameters. One is the mean diffusivity or mean apparent diffusion coefficient, ADC value, or the fractional anisotropic FA values. So we can see a typical red green. From the mean ADC value, mean ADC map, we can hardly see the white matter contrast to the green matter. But on the FA map, we can easily identify the white matter fibers. So usually FA is used to quantify white matter injury during stroke. Okay, this is the perfusion imaging. Perfusion describes the amount of blood delivered to the capillary beds in a block of tissue in a certain period of time. It is closely related to the delivery of oxygen and other nutrients to the tissue. So what I'm doing is using a technique called arterial spin labeling, which is based on the selective inversion of T1 and the global inversion of T1. So we use the two kinds of T1 map. We can calculate the relative cerebral blood flow, which reflects the perfusion. Blood-brain barrier and its function. So the blood-brain barrier is formed by the endothelial cells that line brain territories and are sealed by tight junctions. So the astronauts, astrocytes, parasites, microglial cells, and basement membrane interact with the endothelium of the BBB, providing functional and structural support. A network of, so in sum, BBB is kind of a network of vessels that form a structural and chemical barrier between the brain and the systemic circulation. It protects brain cells from exposure to neurotoxins and other unwanted neuroactive blood-borne agents. So during stroke, the BBB is always broken. So evaluating BBB integrity is a big issue. So to non-invasively evaluate it, we use the method by estimates of the tracer transfer constant. To understand this method, we need to understand the PET-LAC models, which is a highly perfused two-compartment tissue, which means capillary and extravascular, extracellular space. The transport of the low molecular weight semi-conscious agent is unidirectional. So mathematically, it can sum as this form. So the concentration of the conscious agent in the tissue equals to the transfer constant times the integral of the plasma concentration plus current time point concentration of the plasma. So according to this equation, we can see the ratio of the concentration of the tissue to the concentration in the plasma is regressed against the intake rate of plasma concentration over current plasma concentration. So using a linear regression model, we can solve the slope Ki, which is the transfer constant, and the y-intercept represents the distribution volume in the capillary. So in other words, we can evaluate BBB integrity via measurements of leakage rates of intravascular conscious agents such as gadolinium. The next question is how to use MRI to measure the gadolinium concentration. So the theory under the measurement is the accumulation of conscious material in the extravascular, extracellular space of the affected tissue leads to increased longitudinal relaxation rate. So here is the T1 value of as the concentration of Ci equals the T1 values in the absence of gadolinium plus another concentration item. So the concentration is proportional to the changes of the inverse of T1. Here's an example. We sampled the 40 minutes after gadolinium injection and use the linear regression to reconstruct the Ki map. Before moving to the final part, I would like to briefly introduce the rat model of middle cerebral artery occluding surgery, because as I know, probably there are lots of engineering or computer science in this room. So the animal model of ischemia stroke are procedures inducing cerebral ischemia. The aim is to study basic process plus a physiological knowledge of potential therapeutic intervention in this disease. So the people usually use a filament to be inserted through the ECA, go all the way through the ICA, and approach the tip of MCA, and depends on the time. Sometimes people occluded permanently. Sometimes people occluded for a specific time period, like 90 minutes, to withdraw the filament and cause a reperfusion. So I'm going to present an example of multiple model longitudinal MRI evaluating a potential therapy strategy finally. So this result was published on Journal of Neuroinflammation. The idea is proposed by Dr. Yirong. She proposed the attenuation of acute stroke injury in rat brain by minocycline promotes blood-brain barrier remodeling and alternative microglial or macrophage activation during recovery. So here is a stroke recovery monitored by magnetic resonance imaging. So we have we sample data on 4 time points, 2 days after stroke, after ischemia, 1 week, 2 weeks, and 4 weeks. We have 2 groups of animals. One is vehicle, which means experience spontaneous recovery. The other group is received the minocycline injection right after reperfusion. So on panel A, it's anatomic T2 MRI images. So the arrows point to the indicate the ischemia hemisphere. Line graphically demonstrates minocycline can significantly reduce the infarct, particularly during the recovery phase. And panel B is ADC maps. So according to the line graphic bar, we can see the edema and the tissue loss are all significantly different in the ischemia hemisphere. So the FA maps show the white matter protection during the recovery stage. We also applied the ASL map, perfusion map, on day 2, 1 week, 2 weeks, and 4 weeks. We found that the perfusion significantly increased on week 1 and week 2, which may reflect the angiogenesis during the recovery. So this picture shows the blood-brain barrier permeability monitored by MRI. On panel A, the parametric image KI map measured by the dynamic conscious enhanced MRI. The color-coded permeability coefficient maps reconstructed from the MRI demonstrate the region of the higher and the lower permeability. According to the statistic, we found that the minocycline can significantly reduce the permeability of the new vessels. And on the panel C, we use immunohistochemistry to confirm this finding. So the above study is supported by American Heart Association grant in aid awarded to Dr. Yirong, and the Brain MRI facility is supported by NIH P30 to Dr. Liu. And of course, I would like to thank all the MRI core users. Without the users, then without core. That's all I want to present. Thank you.